Yes, good morning, all. Yes. My voice is audible. Yes. My voice is audible. No? Yes. So today we are going to discuss the qualitative structure activity relationship. Simply we call it QSR. Okay. So qualitative structure activity relationship. So QSR generally it is a theoretical part here. So the theoretical technique where it explains and it provides a uh, right? It is provides a platform for the rational drug design here. And nowadays, this QSR technique is one of the prompt method and one of the uh, important technique to develop a drug here. So generally, this particular this QSR technique it provides a relationship between the physicochemical parameters. Generally, we call these are the physical descriptors here and the relation between the physicochemical parameters with the biological activity. And generally here the QSR technique. So in olden days means in the before 1960, okay, so in the 19th century. So okay, in olden days with drug designing, general there is no this kind of techniques here. So where it is a very tough means a tough job to design a drug here or to invent a drug here. And generally in the what is it we call that particular right. So in the the normal approach we call uh, okay the right? So in the traditional methods, the traditional approach, where it is very difficult job to invent a drug compound, and there is means it is estimated that to bring a one active drug compound in the market, so we need to right test nearly 3,000 to 10,000 compounds here, right? So this much amount of compound, like 10,000, 3,000 to 10,000 compound need to design, means need to synthesize to invent means to bring a active drug compound in the market. So we can right, so we can see how much expenditure and how much time, right? So all these are the time. It is a time taking process here, and so much time is in right. So spending on that invention of that drug compound, and there is a loss of there is a great loss of that solvents and chemicals. Okay, all these things here. So the alternate technique was invented, means later the alternate technique was invented with the QSR technique here. So with the QSR technique, it don't needs that chemicals usage of the chemicals here, and it is very speedy process where means instead of that right. So uh, many years like 10 to 15. So here in the traditional approach to bring a active drug compound in the market, we need to spend. nearly 10 to 15 years here. Okay, or sometimes it is more than 20, 15 years also. So nearly 20 years you need to spend on that research to bring a active drug compound in the market. Okay, so where all this time taking process and all this expenditure, uh, right? So invention of that, right, that particular spending of money on that research here is minimized, and it is reduced by this QSR technique. And basically, what is QSR here? So, as I told you, the like QSR is a qualitative structure activity relationship here, and the QSR is it is an attempt in the developing drug in a rational basis here. Okay, so generally the QSR it checks the okay, so it provides a relationship between the uh, descriptors we call that is the physicochemical parameters with your biological activity, right? And you know that some physicochemical parameters like solubility and okay hydrophobicity here and lipophilicity and steric and electronic factors here and the distribution constant, right? So these are the physicochemical parameters like solubility, okay, and pKa means that pKa is where you can say that uh, right. So the acidity like kind of constant here and lipophilicity and steric and electronic factors and distribution constant. So all these are the physicochemical parameters. And generally, all these parameters, physicochemical parameters, they will influence on that biological activity. That's why we will check these physicochemical parameters relationship with your biological activity. Okay, so means where changing of the value of these parameters and how much it is, what is the impact, what is the influence on that particular biological activity, right? So that relationship will be checked in this PSR technique here. And the advantages of these PSR techniques. So basically, we have the main advantage of this PSR technique is so where it provides a very less time here. Okay, so it reduces the time process here. Okay, because in the traditional approach, right? So in the traditional approach, so we need to means spend more time on that work here. So where this QSR technique, so it reduces all that time taking process, right? And it helps in the methods like means it helps the medicinal chemist to reduce efforts in the synthesis of the infinite number of possible analogs with every substrate and a combination of that possible substance here. Okay, so very first advantage of the use of this particular PSR technique is so it reduces the time. Okay, so generally the medicinal chemist where he will always trying to invent a better route to right. So bring a the active or the efficient drug compound in the market here. Right. So for that he will strive for a years. Okay, years time. So generally where if we go with this particular technique here approach, so where it provides very it reduces the time taking process for this invention here. And the second advantage of is so then when an analog is discovered, so which does not fit in the PSR equation, then it may be considered as a lead for further development. Okay, so this is also one of the great advantage of this particular PSR method. So generally, in the QSR technique or the QSR method, where we are trying to derive a relationship between the physicochemical parameters with your biological activity. Okay, in this process, so we are okay. We will take many n number of analogs. Okay, we will consider the n number of analogs to derive that particular relationship here. In that means in that particular process, so generally some, okay, so some uh, analogs may be fit in that particular equation, and some analogs may not fit in this particular equation here. Okay, so in that case, so the compounds are the analogs which are not fit in that equation. So they may be also considered for the uh, for the lead development here. Okay, so there is no waste of that compound, or there is no waste of that molecules here, right? So we can preserve that particular analogs which are invented, or which are find in that outliers generally, right? So these outliers, it may be considered for the further development here, further lead optimization, and it allows the medicinal chemist to say with some confidence that the properties has an important role in the distribution and mechanism of that drug. Okay, so and generally this QSR technique, besides it is a theoretical approach, right? So generally we won't do any experiment here, right? So it is completely dry lab synthesis here. It is not a wet lab. Okay, so it is not a wet lab approach here. It is complete. It is a dry lab approach here. So in this theoretically, generally we'll find out the most efficient analog or the most efficient drug compound here by this approach, and later we'll go with that wet lab here. Later we go with this synthesis of that particular compound which is invented in this route, okay, which is proposed by this route here. So when we get a good values or the good result by this QSR approach here, so we'll get more confident. Okay, so because by by actual process or by experimental approach here, so whatever the compound invented, or whatever the compound is identified as the best active compound here, so in the actual process it may or may not be, okay, it may or it may not be satisfy all the properties like drug properties here. Sometimes it may be okay, it may be satisfying all the properties, or sometimes it won't satisfy that properties here, even though we'll get the confident, because uh, even though by this theoretical approach we got active compound here, so it provides some confidence to the medicinal chemist, or the for the chemist person here, to proceed further, right, so the discovery here, you know? So that confidence will get from this quasar technique. And the quasar studies, it considered how the hydrophobic, electronic, and steric properties of substance affect the biological activity. Okay, so generally this particular QSR technique, right, the QSR technique, where it derives the relationship between the physicochemical parameters with the biological activity. Okay, so this QSR approach, it explains, okay, what is the influence of these uh, factors. Okay, this descriptors are the factors, are the physicochemical parameters. You can say it is descriptors or the factors are your physicochemical parameters. So how they will affect the biological activity. Okay, so how the steric factor is influencing on the biological activity, and how the electronic factors. Okay, steric factors means where the bulkiness. Okay, the having the bulkiness also it may. Okay, so it may causing for the decreasing in the biological activity here, right? And the steric factors, electronic factors. Electronic factors means where the electronegative groups, introduction of the electronegative groups like nitrogen, oxygen, sulfur, oxygen, nitrogen, fluorine, chlorine. Okay, so these are the more electronegative atoms generally. So upon introduction of these atoms on the particular compound here, so how it will be impact on the biological activity, that will be known by this studies here, PSR studies, right? And generally we'll see how much impact is right imposed on that particular biological activity with these factors, physicochemical parameters. So these are the advantages where we can the right. So the main advantage of its PSR studies is so where it reduce the time taking process for this invention of a drug molecule here. Okay, and we'll derive the relationship between the physicochemical parameters with your biological activity. Okay, and it provides more confidence to proceed further the research here. And we'll check the impact of these physicochemical parameters with your biological activity. Okay, so and in the early years of QSR, generally in the 19th century, this is very advanced technique and it is very young technique also, where it is introduced recent in the recent years only, means uh, before the right. So it is past 15 years. Okay, past 15 years. So it is developed very. So before that, okay, so before that, there is no the much development of this kind of techniques here. Okay, and yeah, so here you can see the QSR means the advantage and the uh, benefits of this QSR. Okay, so we'll see the right. So biological activity, the variation of the biological activity with your uh, physicochemical parameters. So we'll take the biological activity. So it is generally it is a factor of your structural molecular or fragment properties here. Yes. And the conditions for the applicability of QSR. Okay. So here the conditions, generally the conditions for this QSR method is we have some conditions like okay, so every method is having its own limitations here. So like that, here the QS are also having some limitations and conditions here. So in that, okay, so where the first condition or the limitation is where the selection of appropriate chemical series is important to develop QSR models to obtain valid results here. Okay, so in this QSR technique, okay, so if you want to go with this QSR technique, so the selection of to see are the set of the components. So when molecules are the space are equal, right? So if we so further So when you are going to select the set of series compounds here, so you see that the feasibility of that compounds. Okay, if by theoretical approach, by QSR approach, so if you get a good valid results here, then whether these compounds are right feasible or are suitable for the synthesis here, and means you have to okay means you propose a particular scheme for that synthesis of that compound here. Okay, so whether the means the reagents are available for this synthesis of this one. Okay, that is a synthetic strategies. You okay, so you build up a synthetic strategies for the getting of that okay that target molecule here. Okay, so the condition is you have to check the right the means you selection of the appropriate chemical series is important here, because we have so many chemical series like variety of molecules are available here with different core structures, like we have the hydrocarbons, we have the heterocyclic compounds and the natural products here. Okay, and three-membered, four-membered, five-membered cells. Okay, so and bicyclic, tricyclic. So all these are the variety of chemical structures are the chem compounds are available, right? So in the synthetic banks here. So while you are selecting these series of compounds, see that okay, generally in this QSR technique, so where we go with the some modifications, isn't it? So we'll take the existing molecules here, and we'll go with some modifications, right? And when you are going with these modifications, you see that for the back getting of that compound, the feasibility of that compound, that is important here. So the appropriate chemical series selection is important condition for this applicable for the QSR here. And the biological activity of this series of compounds should be related to the physicochemical parameters being considered here. Okay. And you see that the compounds which are selected, the series of compounds which are selected, so they must be relates to your biological activity. That means where your compound are right, so whether they are okay showing the biological activity or not, and they must having the right, so while you are selecting the series of compounds here, so the biological activity values must be reported, right? The biological activity values must be reported here. So without biological activity you won't can't right, so go for this QSR studies here. So it must be relates with the biological activity. And the selected chemical series should consist of compounds that exert biological activity via a common mechanism modeled by a QSR equation. Okay. So generally in this QSR technique, so we will try to build a equation. We'll generate a equation between the physicochemical parameters and your particular biological activity here, right? And that particular compound, right? The series of compound must be having a good equation with your biological activity. And a wide range of relevant compound must be selected to assay its utility. Okay, so in the QSR, because it is a random technique here, okay, the QSR technique generally won't means no need, there is no condition to select a particular compound here. So in this QSR technique, so randomly you can select the series of compounds. Okay, so we'll take the series of compounds here. So in order to get the better precise values here, to get the good result, you need to take a wide range of compounds. Means the more number of, okay, the more number of compounds will uh, have the probability for getting good results here. Okay, so if that set of compounds is having more number of compounds, then it provides some good results. Because, for example, while you are proceeding with the QSR technique here, the QSR method, so if you select 10 compounds here, so in the 10 compounds, the probability for getting results, right, is less. But if you select 100 compounds here, so there is a possibility for getting means getting the good result here. Because okay, for example, here the 90 compounds are outliers here, then 10 compounds, at least the 10 compounds may uh, okay, it will be selected for this further steps here. So where the selecting of less compounds, right, selecting of less number of compounds in the series, right, so it won't the probability for the getting the result is less here. And selecting of more number of compounds, the probability for getting good result is more here. Okay, so you have to select okay, relevant compounds in large number here. And the parameters used in the QSR should be meaningful and easily interpretable in the physical terms. So generally, okay, the parameters which are used in this QSR technique, like lipophilicity, hydrophobicity, okay, and your what is that called, that partition coefficient here, okay, and steric factors, electronic factors. So all these are the already predicted parameters here, and generally they are good understanding with your mathematical equations here, right? So the parameters should be meaningful generally. So and all these parameters are having their own descriptions here. So the descriptors are much explained and much okay, reliable here. And the selected descriptors should provide valuable insight into the mechanism. So generally, they will provide some valuable information here. Because, for example, if you get that, if you take the partition coefficient here, okay, so the partition coefficient, so where it rho, the symbol is rho here. So where it explains, okay, it explains that particular distribution property of your drug compound. You know that the drug is having right, the drug properties are there, are five properties are there, ADME properties, okay, admit, like absorption, okay, uh, distribution, metabolism, and excretion, and toxicity. So these are the five properties, okay, these are the five drug properties here. So any ideal drug or any good drug must satisfy all these five properties here. Okay. So, where this descriptors should provide valuable insight into the mechanism and high quality and reliable biological data. Okay, so generally, where we'll collect that biological activity of the compound from the literature. Okay, and generally, the if that particular article is published in the literature here, so generally it is okay, right. So generally, it is having some right quality, right. So because they will publish, okay, the publishers will publish the research article by seeing all the possibility for this one, right. So obviously the results which are taken from this literature, right, so it is worthful here. And the compound must be pure. Okay, so while you are selecting that set of series from the literature here, so you see the purity of that compound, right? So generally they will provide, okay, provide the purity of percentage and yield, melting point, all this. Okay, so all the data should be collected from the literature here, and it all this data is provided in the literature. Okay, so while you are selecting the compounds or the set of series from the literature, you have to check these properties also. Okay, these qualities also here. And concentration must be molar and not in weights. So generally, we'll take the right the values. The concentration is in the molar values. We won't take in the weight here. Okay. So in the synthesis, okay, in the synthesis, the yield. Okay, so we'll calculate the yield in the weight here. But in the biological activity in the right in the QSR technique method, so the biological activity will be expressed in the molar. And the last one is a QSR study is done only for a set of analogs of a lead, and different members in this study different from the another, which is respect to nature of the substance, to position of the substance. Okay, so here generally the QSR technique is generally the QSR technique won't apply the QSR technique for the single molecule. Okay, so most probably we'll apply this QSR technique for a set of molecules here, for a series of molecules. No, this is not applied for the single molecule here. Right? So we'll take the set of molecules by taking some different analogs here. Okay, by taking the different analogs by changing the substituents. Okay, and atoms in that particular core structure here. Uh, so here the steps we have the means how to approach this QSR method, how to go with this QSR. So here you see the selection of biological activities of interest. Right. So once you interested in the QSR method technique here, so first you have to select the series of compounds which is provided, right? Which is having the biological activity. Okay. So and generally we know the biological activity various types means some antibacterial activity will be there, anti-cancer activity will be there. Okay, antifungal activities will be there, anti-inflammatory activities will be there. So all these are the biological activities here, right? So first you select, okay, first you select of your select the biological activity of your interest on which you want to go with this PSR, right? So approach here, right? For example, if you want to, if you are interested in the anti-cancer activity, so you search the relevant series of compounds in the literature, and you take that compounds. Okay, for the you consider the compounds for that PSR approach here. So the first step is a selection of biological activity of interest. So in this step, you have to select your interested biological activity like anti-cancer or anti-fungal or antibacterial. So that thing you have to select here. And the choice of structure class within the class, all the structure compounds are similar and function according to the same mode of action here. Okay. So once you are selected the you are interested biological activity, like if you are selected the antibacterial activity here, for example, you are selected the antibacterial activity, right? So you select the series of compounds from the various literature which are having the same core structure, right? For example, if you are selected the naphthalene derivative here, okay, so you okay, you select or you search the naphthalene analogs only, right? The naphthalene is the core structure for your interested biological activity. Then you have to, right? You have to select the variety of molecules which are means variety of analogs, right? So naphthalene analogs from the various research articles here, or you can right, so you can go with the designing of variety of substituents on that naphthalene here, right? So here the choice of structure class, within the class all structure compounds are similar here, and the choice of structural features to be varied, right? The choice of structure features. So you see the structure features. For example, if you are selected the naphthalene as a core structure here, right? And the naphthalene, the substituents, the naphthalene is a core structure, and we are taken some series of compounds with the different substituents on that naphthalene here. So all these naphthalene analogs, right, must showing the values generally, right? So for example, if you take the alpha naphthal, its value will be varied with the alpha beta naphthal here, right? Because where you can see the position of that OH group on the naphthalene is different. Where in the alpha naphthal, where the it is on first position here. Okay, so and in the beta naphthal, where it is in the second position. So the changing of the position also, it right, some changes will be there. So means if you take all the, for example, if you take alpha naphthal, beta naphthal, both are showing the same activity, then there is no use of that compound. So you avoid such kind of compounds must be avoided here, right? So the series of compounds, the analogs which are selected, they must show the different means they must show the activity must be same, but their the activity values must be varied here. It will be different here. Okay. The features, structure features to be varied, and the quality to sorry, quantitative description of structural variation and the choice of PSR model, and synthesis and biological testing, right? So after all these going with this technique here, so generally we get some uh, compounds in the inlayers. Like some compounds will be successful compounds are obtained in this one. Then those compounds must be synthesized, and you again you check the biological activity. And the selection of physicochemical properties to be studies. So obviously we'll right. So we'll check the physicochemical parameters for each and every analogs in the PSR, right? So if you take 20 analogs, naphthalene analogs in case, right? So we will check the variation of the uh, variation in the values. Okay, biological activity values for each and every analogs here, right? So it will be studied, and certain substance must be should be avoided in the initial study, which might ionize, such as COH, NH2, and SO3H, etc. If possible, compounds which might easily to be metabolized should also be avoided. Okay, so generally in this particular PSR studies, right? So we'll check the by a relationship between the, right. So the QSR provides the relationship between physicochemical parameters with your biological activity, right? So what are the biological activity here? It is anti-cancer activity, anti-bacterial, all these are biological activity. And what are the physicochemical parameters in this case? So physicochemical parameters are like you see the solubility here, okay, solubility, and partition coefficient, electronic factors, steric factors. Okay. So all these are the substituent constant also. So all these are the physicochemical parameters here. And while you are considering these substituents or the series set of series here, compounds here, so see that some group of right, some groups, some functional groups must be avoided. because these groups are easily ionized here. Okay, so these groups are easily ionized. So in the drug compound, okay, so before the metabolism, right, before the showing its activity at the site of action here, if gets ionized here, then it is losing its biological activity, right? So if it is ionized here, so it losing its biological activity. Then it becomes inactive, chemically inactive here, biologically inactive here. So to avoid such properties, to avoid such difficulties here, so you have to, okay, you have to avoid the such groups like COH group, NH2 groups. So these are easily ionizable because you see these are the polar groups here. These are the polar groups. So they will easily ionize. Okay. So you better to avoid all these groups in initial stage only. Right. Next, the graphs and equations in the VSS. Yes. So generally, we'll know the right the precise the activity range. Okay. So the better biological activity and the relationship between the descriptor with your biological activity with right. So by the graphs only. Okay. So if you draw a graph between the by taking the descriptor in one axis and your biological activity in another axis, if you draw that, right, then the relationship between these two factors will be known. Okay, so here generally we'll use the graphs and equations in the QSR studies. Okay, so we'll use the graphs and equations in the QSR studies. And generally the yeah. So in these graphs, we'll take uh, biological activity as 1 by log 1 by C value on y-axis. Okay, biological activity is taken as the log 1 by C, and it is shown on your y-axis here. And in x-axis, various descriptors are the physicochemical parameters, are the factors here, like hydrophobicity. Okay, uh, what is it? Steric factors, electronic factors, partition coefficients. Okay, so all these other descriptors will be taken on the x-axis here, and we'll derive a equation here, graph here. Okay, and here in this particular relationship in the graphs and equations, right? So in the graphs, generally we get the two kinds of graphs here. So one is a linear correlation here and parabolic correlation, right? So where in this graph you can see where the biological activity versus physicochemical properties, where the biological activity is denoted with the log 1 by C is taken on the y-axis here, and the physicochemical parameters is taken on the x-axis. One shown with one example like log P value here. Log P, it is a partition coefficient here. Okay. But in the first graph, you can see the straight line, that is a linear correlation. Means with increase of your log P values, the way the biological activity is going to increase, right? And your second graph is expense where, so here also we are taking same descriptors like log 1 by C, that is the biological activity is taken on your y-axis, and the log P value is taken on the x-axis here. And we are getting the parabolic relationship here, parabolic correlation. In the first case, we got the linear correlation here, the straight line, and in the second case, we got the parabolic relationship. Right? And when you get the linear correlation and when you get the parabolic correlation. So we'll see. Yes. So physicochemical parameters. So as we discussed in the starting here, so we have the variety of physicochemical parameters. And the QSR, basically the QSR, it checks the, okay, it provides the relationship between the physicochemical parameters with your biological activity. Okay. And in the physicochemical parameters, we have like solubility, okay, acidity constant, pK value here, and lipophilicity, steric factors, electronic factors. So, and their symbols is given in this table one. You can see here. You can see that physicochemical parameters like hydrophobic parameters. So, in the hydrophobic parameters, we have partition coefficient. Okay, so here the partition coefficient where the log p value, that means partition coefficient is shown with the log p, and pi. Yeah, the pi is a substituent constant, and chromatographic parameters. It is solubility is delta here. Okay, and elution time in the HPLC is log k. And then we go with this electronic factors. It is ionization constant, pK, and sigma substituent constant here, the sigma, right? And spectroscopic chemical shift values is delta ppm, and the resonance effect is R here, field effect is F, ionization potential is I. Right? So all these are the symbols for various parameters, and the steric factors also given, like top steric substituent constant is ES, and van der Waals radii is BL here, and interatomic distance is MR, and molar refractivity is MB here. Okay. So all these are the some listed parameters with their means denotation here. Okay, the symbols. Yes. So first we'll see the hydrophobicity or the lipophilicity. So generally that hydrophobic nature. Okay. So where the drug compound, right? The drug must have the good hydrophobicity. Right? The hydrophobicity, what is hydrophobicity generally here? Hydro means water here. Okay, hydrophobicity is, hydrophobic nature is the water fearing, water hating here. Okay. So the drug compound must have the good hydrophobic nature. Then it's right. So absorption properties good. Okay. Yes. So hydro means water here, and probe means fear. So water fearing is other water. Uh, what is a disliking, or we can say hating, is a hydrophobic nature here, or we call it is lipophilicity. Hydrophobicity or the lipophilicity. If any compound is hydrophobic, so it is lipophilic. Lipophilic means lipid loving or the lipid attracting here. Okay. So here the hydrophobicity, it represents a tendency of the substrate to repel water and to avoid the complete dissolution in the water. Okay. So your the drug compound must not dissolve in the water, right? So which is not dissolved in the water is, and some partial solubilities are not generally. So it is explained by your lipophilicity or the hydrophobicity. And yeah, so obviously it is hydrophobicity is one of the most important physicochemical parameters associated with the chemical compounds here. And this will means the hydrophobicity or the lipophilicity is explained by that partition coefficient factor, right? So partition coefficient, nothing but it is a ratio, right? So partition coefficient, it is a ratio between the concentration of the compound or the drug compound in the uh, N-octanol by concentration of the drug compound in the water. Okay, so partition coefficient nothing but, so it is a ratio here. It is a ratio between the concentration of the drug compound or the solubility. We call this concentration of the solubility of your compound in the N-octanol. N-octanol, it is organic solvent here, and the concentration of your compound in the or the drug compound in the water, where the water is a polar solvent and N-octanol, it is a non-polar solvent. So we'll check the it is a ratio. Okay, so it is a ratio, and we'll check the solubility properties in the both different solvents, like right, N-octanol and your water. And it is one of the good parameter which explains the absorption property of your drug compound. Yeah. Yes. And you see that partition coefficient is an important means of predicting hydrophobic nature of your drug compound. Yes. And the consequences of this hydrophobicity, you can see. This coefficient is normally calculated in the form of its logarithm base 10, log 10 here. And it P range 10 power and its value, it is ranging from 10 power 4 to 10 power 10 power minus 4 to 10 power 8 here. Yes. Now the conditions are the consequences here. With the hydrophobic compounds, hydrophobic nothing but with the low polar compound. Okay, so highly soluble in the octanol will have the high P value. Okay, so if log P is log P is greater than 0, right? Log P is greater than 0. So that means that compound is highly soluble in the octanol. And log P is less than 0 here, it is highly soluble in the water. Right? Log P value is less than 0 here. So where it is soluble in the water. And by varying the substance in the lead compound will produce a series of analogs having different hydrophobic P values here. Okay, so in this, yes, so first we'll check the hydrophobicity or the partition coefficient of that compound by this equation. By checking the solubility of your compound in both solvents like water and octanol. Right? Then we'll know how much solubility is there in the octanol, how much solubility is there in the water here. Okay. Then depending on our requirements, right? So depending on our requirements, we'll adjust the log P value, right? So we can derive the log P value by changing the substituents here, by changing the substituent. Okay. So for example, here where if the compound is right, the compound the drug compound is, it is highly soluble in the octanol, right? Highly soluble in the octanol. Then if you want to lower that octanol solubility, in that case you have to remove the polar groups here. Sorry, you remove the you introduce some polar groups on that. You introduce the polar groups on the particular drug compound. Then what happens here? Where the octanol solubility will be decreases and the water solubility will be increases. Okay. And for example, if your compound is highly soluble in the water, okay, then you try to introduce the less polar substituents here, right? If any existing more polar substituents are there, then you remove that substituent. For example, if any acid groups and any amino groups are there in the along with your drug compound here, when it is then obviously that polar, if the compound is carrying the polar groups here, so obviously it is soluble in the water, because in the solubility principle, you know that like dissolves like here. Okay, so polar compounds soluble in the polar solvents, non-polar compounds soluble in the non-polar solvents. By that principle, where it is soluble in that water. So if we don't want to more soluble in the water, in that case, you remove the polar groups in the existing compound and you introduce the non-polar groups in that. Then you can see the increase of the octanol solubility, right? And decrease in the water solubility here. By in this way, you can manage that solubility, or you can manage that log partition coefficient. And by varying substance in the lead compound will produce a series of analogs having different hydrophobicity and p-values. A lot P to be determined for all the analogs in the QSR study. So once you generally QSR model is generated for series of compound, right? For single compound, the QSR model cannot be generated generally, right? The QSR model. So you need to take a group of compounds, a series of compounds. Okay. So how to calculate the log P value for all the series of compounds? Okay, because if, for example, we are taking n set of compounds. For example, that n is 10. So 10 number of compounds are taken for this, consider for this QSR model here. So you have to check the log P value. Log P nothing but your partition coefficient, isn't it? Solubility, solubility here, a factor, or the partition coefficient. So you have to check the solubility for all compounds present in the set or the series here. And the partition coefficient graphs. So generally in the partition coefficient graphs is drawn, right, by taking the biological activity, that is the log P 1 by C. So log 1 by C is on y-axis and okay, so where that some descriptors is taken on the x-axis here, right? So by taking this equation, we'll generate that. Okay, we generate that graph. Okay, and that graph is having two nature, like where the linear graph, right? Linear relationship, and the particular parabolic relationship here. And linear relationship between log P and biological activity. So when we get that linear relationship and when we get the parabolic relationship, we can see. Yes. So generally, yeah, here is a linear relationship. Okay, so generally where that with increase of the log, okay, log P values, other descriptors here, where the biological activity will be increases for a optimum, okay, y value here, okay, for a certain point. By reaching that certain point, we call that is the optimum point here. Okay, so by reaching that optimum point, where we can see the decrease in that, right? So biological activity, or it will be stark constant here. There is no change in that one, or decrease or the constant. These two things we will observe. Okay. And generally for all kind of drugs, this uh, linear relationship graphs will be obtained, right? So linear relationship graphs are very common for all kind of drugs here. Okay. And to check this, by taking a 40 compounds here. So by taking a 40 compounds, they will check the uh, relationship between for this compound with your biological activity here. Then they got this particular linear relationship here. Okay. And the non-release. So here some okay, so some limitations are observed during this linear relationship here, where the high log P is poorly soluble in the aqueous phase. Okay, high log P means high log P. When you get the high log P values, so when it is more soluble in the octanol, right? When it is more soluble in the octanol, we get a high log P value. Means log P is greater than 0. If you get the log P is greater than 0, generally it is highly soluble in the octanol, or it is poorly soluble in the aqueous phase here. And high log P hydrophobic drugs, so often more susceptible to metabolism and subsequent elimination, right? So the drug compound, the ideal drug compound, right? Okay, the ideal drug compound must have the uh, higher log P values. Then it is more okay, it is more susceptible to your metabolism and elimination properties here, right? And really linear relationship here. So non-linear relationship generally, where we get this kind of relationship graph, where initially the biological activity will be increases, and after reaching that optimum point here, so where the decrease in the biological activity will be takes place. So this kind of relationship is avoided, right? So if you get this kind of relationship, okay, so actually here after reaching that optimum point, it must be become neutral. It must be neutral here. Okay, but here it is what is happening. It is the way the decrease in the biological activity is taking place here. So generally, this kind of relationship is rarely observed for the drugs here, and where the CNS depressants, okay, for CNS depressant and narcotic drugs, and that is what is that anesthetic drugs here. So we'll observe this kind of graphs here, right? So because in the anesthetic drugs or CNS depressants, okay, so where during that right, so in the what is that uh, anesthetic drugs here, for example, they are taking up some surgery here, so they will give that anesthetics here. So initially okay, so initially they won't have the sensation of the pain here. Okay, so that after completion of that surgery or after a particular time here, so its effect should be reduced. So the activity will be decreased. That's why you get the decrease in the activity. So we get the parabolic kind of graphs here. Okay. So some selected drugs, some kind of group of drugs, right? Class of drugs here. So we'll get the parabolic relationship. And in many cases, and for in general, we get the linear relationship only for the drugs activity. And of course, this is the Hans Fujita constant. substituent constant. We call this substituent constant or the Hans-Fujita constant. Yes. So here the partition coefficient, it can be calculated by knowing the contributing that various substances make to hydrophobicity. That contribution of a to the partition coefficient of the molecule is known as the substituent lipophilicity or the hydrophobicity constant. Okay. So here that particular partition coefficient is calculated for the right the substituent uh, for this particular core structure drug molecule. Right. And here, if we want to change the right lead compound here, lead modification, then how much impact is there for a particular introduced substituent on the biological activity, that will be known by that will be known by your uh, this particular substituent constant here. And generally it is denoted with pi here, substituent constant or the Hans-Fujita constant here, and pi equal to log px minus log ph here, right? So where the log ph is the partition coefficient of your standard compound. So it is a standard value which is provided in the literature, means hydrogen. Okay, the partition coefficient of the hydrogen normal. And px is the substituent, various substituent here, derivatives. Then we'll see the means some standard values are given for this particular substituents here. For example, if you take this, okay, here for the aliphatic and aromatic, two different series, means two columns are given, and their impact, okay, the impact of your substituent is given. Like, for example, the substituent is hydrogen. So it is a very standard value here. Okay, so this is a reference value. The hydrogen is a reference value. So you can, whose value is 0. It is a standard. So reference value here, whose value is 0. When this hydrogen is replaced with the methyl here, and that methyl is on the aliphatic system, like Rx, X equal to methyl, then its value is 0.50. And if it is on the aromatic system here, then its value is 0.56. You can see some increase in the aromatic system. And if the hydrogen is replaced with fluorine, if it is introduced on the aliphatic system, so its value is minus 0.17 here. If it is introduced in the aromatic system, its value is 0.14. This decrease, because you see the fluorine is a electronegative group here. So where it is a decrease in the aromatic system here. And the chlorine, if it is introduced on the aliphatic system, its value is 0.39. And on the aromatic system, it is 0.71 here. Likewise, hydroxy group, it is minus 1.16 here on the aliphatic system. And an aromatic system, it is minus 0.67. Okay. And the value is not available, or no impact on this aliphatic system. And an aromatic, where it is impact is minus 1.23. And nitro group also, where it is shown the minus 0.28 impact on the aromatic system. And the methoxy group is 0.47 on the aliphatic system, and minus 0.02 is on the aromatic system here. So these are these values guides us to which substituent need to considered, or which substituent you need to take for this to generate a QSR model or the equation here. Right. For example, if the value is the hydrophobicity value or the partition coefficient value is going to decrease, in that case, you take the value, means the substituent value whose value is more, right? Then you can see the increase in the partition coefficient value. If the partition coefficient value is increased, then obviously that hydrolipophilicity or the hydrophobicity going to increase here. Then generally that drug needs that property. Okay. Yes. So these values, well, if your substituent values are given, and these values are guiding us to, okay, guiding us to which substituent is increasing the partition coefficient value, or which means consideration of the substituent which is going to decrease in the partition coefficient values here. Next, the electronic fact parameters. So here the electronic parameters with introduction of the negative groups, which is able to influence on the biological activity. Okay. So here you see that. So the electronic parameters indicate the influence of polar characters of your drug on the biological activity, and the metabolism and elimination pattern of the drug, and the drug receptor interaction, pharmacodynamics. Okay. So here in the drug, right, in the drug chemistry, okay, the drug chemistry where there are four important properties which is shown better way by your drug compounds, like ADME properties here. So ADME nothing but absorption, okay, distribution, metabolism, excretion here, and these values are varies by the groups here. So here this electronic factors, right? The electronic factors like the electronic with the electronegativity groups here. Okay, more electronegative groups, or you can say these are the polar groups here, right? So the polar groups, they will influence on the biological activity, and they will play a very important role in the uh, metabolism and elimination private pattern of the drug here, right? And these are the means the drug must be having the satisfying of these properties only. Okay, so the drug must be having good absorption property here, and the drug must have the good distribution property, and it must have the good metabolism property, and good elimination property. Okay, so that all these four properties will be depends on the all these factors like partition coefficient, solubility, partition coefficient, and your electronic factors, right? Substituent constant, all these factors is influence on the drug journey. We call that is a pharmacodynamic here. Okay, pharmacokinetics and pharmacodynamics. So pharmacokinetics explains the journey of the drug here, and pharmacodynamics explains the interaction of your drug compound, binding of your drug compound. So drug receptor interaction, pharmacodynamics, like how efficiently it is bind with your receptor, right? So generally the drug chemistry, right? So the drug chemistry principle is the internal principle of your drug chemistry is where the drug receptor interaction. So when the means you receptor nothing but your proteins and enzymes here, and carbohydrates, so ion channels, all these are acting as receptors. So when the drug compound is bind with your receptor active site, then the physiological action will be takes place, and it release some chemical messenger, and that chemical messenger will be operating some kind of biological functions here. So that is a principle of your particular drug chemistry. Okay. So here this the electronic factors, it may influence on the drug receptor interaction also, and it may influence your metabolism and elimination pattern also here. Okay. So here the commonly used electronic parameters it is shown in this particular table one here. Like in the table one already we have seen the electronic factors. Here we can again I will repeat all this. It is yes, here is electronic factors. You can see where electronic factors are the ionization here, P and sigma substituent here, and resonance effects like R, field effects, ionization potential I, right? And where it is atomic net charge Q and QT, all this. Okay, but the important factors are the ionization constant here, pK value, sigma substituent, and resonance effect, field effects. So these are the important electronic factors here, and they will influence, they will impact your particular solubility pattern, elimination pattern, and distribution pattern. Yes. Yes. So here you see that particular. Okay. And the impact of that electronic groups is explained by the Hammett equation here. And here the, you know, the Hammett equation, right? And here you see that sigma, right? Hammett substituent constant, it is a sigma here. And in this one, the value, okay, the value of the various means various groups under this electronic factors. So you can see the uh, para substituent and the meta substituent here. Okay, in the Hammett equation, we can consider the para and meta substituent only. We won't consider the ortho substituent because the ortho substituent causing for the steric repulsion here, and it makes that compound unstable, right? Because where the substituent is for the substituted benzenes here. So the impact of the ortho substituent and the meta substituent, you can see. For example, here the oxide ion, right? Like pin oxide, right? You take pin oxide ion here. If it is at para position, sigma para, so where its value is minus 0.81 here, and sigma meta where minus 0.47. Okay, and you remember that there is no okay, there is no impact, there is no effect of your ortho substituent here, because ortho substituent won't consider, and generally we won't keep the ortho substituent here because the ortho substituent causing for the instability of your compound, it making the compound unstable, the drug compound is unstable. That's why the ortho substituent not be considered. And the NN dimethyl group, impact to para position, sigma para is minus 0.63 here, and to meta it is minus 0.10. OH group you see minus 0.38, 0.13 here, and methane and carboxylic acid also you can see 0.11 and 0.02 at meta position. And for fluorine, you can see the 0.15 at our para position. Okay, because here the para it's sterically less crowded here. Okay, para position it is sterically less crowded, so you can see the values changes in the values here, right? Para and meta position. And for fluorine, chlorine, and bromine, you can see the difference of the substituent at means present on the ortho position as well as your para positions, right? And carboxylic acid substituent also you can see that at ortho position, at para position it is 0.44 and at meta position 0.35, right? So you can see the difference between this difference between the meta and para is where your meta substituent, right? The meta substituent where it is it experience some steric repulsions here, and para substance it is relieved from the right. It is relieved from your s- that steric repulsion here, because the separation, right, the gap between the substance and your that para fourth position is very large here. In this how the nitro group also you can see where the at meta it is 0.81, at para sorry, at para 0.81, at meta 0.71. Okay, so these values guides us to which substance we need to consider for the getting the better uh, value in order to generate a QSR model. Okay, so all these are the values. So means depending on our requirements. For example, if you want to increase the value, right? If you want to increase the pi value here, what is pi here? Substituent constant. Pi nothing but your substituent constant here. Hamed substituent constant. So if you want to increase the value, then you pick up the group. You pick up the group according to increase, and you substitute in this what is that in this formula, like pi equal to log px minus log ph. Okay, px is your log px is your the various groups uh, log p value here. So it is given in this table. So you pick up that, and you can get the your required equation. Okay. Next, Hammett substituent constant here you see. Next, application of substituent constant in the QSR studies. Right. So here in this part, here one example is given, like the action of enzyme inhibition. Right. So when this particular right the amino acid, right, here the enzyme with the hydroxy group which is taken. So with the hydrolysis, the rate of hydrolysis is explained in here. So you can say when this particular compound, right, is taken, like this is the normal, the reference one where there is no hydrogen, means there is no substance at the para position here. And when the para position is substituted with the methyl group here, where the rate of hydrolysis is slower, means it is decreased here. And when the nitro group is taken at para position, okay, so where the nitro group, it is more electronegative group here. Methyl group is, it is less electron, means it is a plus Me group, and nitro is a minus Me group here. So when the minus Me group is taken, where the hydrolysis rate of hydrolysis is increases, because the NO2 group is, nitro group is, it is electron withdrawing group here, electron withdrawing group. So it withdraw the electron, then the where the cleavage of this phosphate linkage is takes place easily. Okay, so the effect of that substituent. So depending on our requirements, you have to select the suitable substituent, and you incorporate with your benzene derivative here. Then you see the values, and here the some graph is given, means the where the values. Okay, so how the impact of these substituent, various substituent electronic groups impact on your biological activity, it is given. For example, here the methoxy group is taken, right? So here the methoxy nothing but where it is plus I group here, plus Me group. It is electron donating group here. So no change in, means the where very less increase in the biological activity here. And chlorine, bromine, it is somewhat more electronegative group here, minus Me groups. So where some increase in the biological activity here. And carboxylic acid, it is again it is polar group, or the two oxygens means more electronegative groups are there. So where increase in the activities takes place here. Like nitro group, it is withdrawing group here. Again, the more increase in the biological activity. And sulfonyl, methyl sulfonyl group is there. So it is more electronegative. So higher degree of increase in the biological activity. So these substituents guiding us to uh, which group need to considered for the increase in the biological activity here. Right? This is substituent constant. And the remaining factors, remaining sorry, the remaining physicochemical parameters will be explained in the next class. So I am stopping here.